All right, ready for a deep dive into some really cool research.
Absolutely.
Okay, so today we're looking at bone repair. Specifically, a new biocomposite material.
Interesting.
It uses something called demineralized bone matrix and magnesium.
Okay.
Like, imagine if we could ditch the metal plates and screws
Yeah.
and use a material that helps your bone heal and then just, poof, disappears.
That's exactly what Dr. Carmen H. Escalera and her team at the National Autonomous University of Mexico are working on.
Okay.
Their research, which was published in the Journal of Materials Research,
Mm-hmm.
really tackles a big problem
Yeah.
with the way we fix bones right now.
Because those metal plates and screws,
Right?
they work,
Yeah.
but they're not perfect, are they?
No, not really.
I mean, who wants another surgery just to take them out?
Nobody.
And then there's that whole stress shielding thing.
Right.
Can you explain what that is?
Basically, it's like if you were trying to dead muscle, but you were using a machine that did half the work for you.
Oh, so your muscles wouldn't get as strong.
Exactly.
And that's what happens with metal implants.
Yeah. They're so much stiffer than bone.
So they take on all the stress.
And the bone doesn't get the work out. It needs to heal properly.
So metal implants are like overprotective parents,
Kind of.
shielding the bone from the tough stuff.
Exactly.
And that's where magnesium comes in.
Right.
Because it's biodegradable.
And its stiffness is way closer to bone than metal.
Oh, so it's all about finding that Goldilocks zone.
Yeah.
Not too stiff, not too soft.
Just right.
But how do you even make a bone implant out of magnesium?
Well, that's where things get really interesting.
Oh, okay.
They combine magnesium with something called demineralized bone matrix.
DBM.
Yep, DBM. It comes from bone, acts as a scaffold,
Hmm.
like a framework.
So the DBM is like the blueprint and the magnesium is the building material.
You got it.
But can DBM even hold a broken bone together on its own?
On its own, not really. But when you combine it with magnesium,
Yeah.
now you have something strong and biocompatible.
And then as the bone heals.
The magnesium just degrades away,
Yeah.
leaving you with nothing but healthy bone.
That's incredible.
It is. It is.
But how do they even combine those two materials?
It's a very precise process.
Yeah.
It's called liquid metal infiltration.
Whoa.
They basically inject the porous DBM with molten magnesium.
That sounds,
Tricky.
yeah.
It is.
Like, I imagine the scaffold could collapse or the magnesium could, like,
React in unexpected ways.
yeah.
You're right. Those were some of the challenges.
Hmm.
They actually tested 2 types of DBM to see how it would affect things.
Two different types.
Yeah. One had a special carbon coating and the other didn't.
Interesting.
The results were pretty different, actually.
So what happened?
Well, let's get into that.
Okay.
I think we need to take a closer look at the microstructure
Okay.
and see what's going on at that microscopic level.
Let's do it.
You won't believe what they found.
Okay. Okay, so before the break, we were talking about those two types of DBM
Right, right.
and that molten magnesium. It's all very precise.
Very.
So what did they find? What happened when they put it all together?
Well, the first thing they looked at was the microstructure of the composite.
Microstructure.
Yeah, we're talking zooming way into like the microscopic level.
Gotcha.
Where you can really see how the material behaves.
So what's going on down there at that tiny scale?
Okay, so picture this.
Yeah.
You've got all these intricate pores in the DBM.
Right.
And the molten magnesium fills all those little nooks and crannies.
Oh, I see.
And then, at the boundary between the magnesium and the DBM, a special layer forms.
What is it?
Mostly magnesium oxide.
MgO.
Yeah, MgO.
Okay.
And that MgO layer is really important.
You mentioned that before about the MgO layer.
Right.
And that the carbon coating,
Yeah.
it changed the MgO somehow.
You have a good memory? Yeah, so the carbon coating on one of the DBMs, it actually prevented the magnesium from fully reacting with the DBM.
Interesting.
So what happened was it created a thinner MgO layer,
How thin are we talking?
like 10 to 20 micrometers.
Okay.
But the composite made with the non-coated DBM,
Yeah.
that one had a much thicker MgO layer.
Oh, wow. So like twice as thick.
Almost, closer to 40 micrometers.
And that made a difference.
Huge difference.
Really?
It affected the strength of the composite in a big way.
I would think a thicker layer would make it stronger.
You'd think so, right?
Yeah.
But it's not just about how thick the layer is. It's about how well it bonds everything together.
Okay.
So in the composite with the carbon coating,
The one with the thinner layer,
right, that one had a much stronger bond between the magnesium and the DBM.
like a really tight seal.
Exactly.
So a thinner layer actually made it stronger.
In this case, yes.
What about the other composite?
the one with the thicker layer.
Yeah, was it like super weak?
Well, no, it wasn't weak,
Okay.
but it was almost half as strong as the other one.
Wow, that's a big difference.
It is.
So this is why material science is so cool.
I know, right? There's so much to learn.
You never know what you're going to find.
Okay, so we've talked about the structure and the strength. But what about, like, how it behaves in the body?
That's a great question.
Like how it breaks down and what happens to the byproducts?
That's where things get really interesting.
Okay, tell me more.
Well, the way a material breaks down, it can tell you a lot about how it's going to perform.
So how does it break down?
Okay, so with the composite that had the thinner MgO layer,
Yeah.
the fracture.
It's a break? Yeah.
Yeah, it tended to travel along the interface.
Between the MgO and the magnesium?
Exactly.
Like a clean break.
Pretty much, yeah.
And what about the composite with the thicker layer?
That one was a bit more...
Messy. So it didn't break as cleanly. No, it was more erratic. The cracks went through the MgO layer and the magnesium.
So is one better than the other?
Well, that depends on what you need the implant to do.
Okay.
If it needs to withstand a lot of stress,
yeah,
then you need to know how it's going to break down.
Gotcha.
And that's what they're still figuring out. It's all about understanding how the material behaves under pressure.
This is all so fascinating.
It is.
But we still haven't talked about how it breaks down in the body.
Right.
You mentioned something about localized corrosion before.
I did.
Can you explain what that is?
So, localized corrosion.
Yeah.
It's a type of corrosion that happens in specific areas.
So not the whole thing.
Right.
Why does that matter?
Well, remember how we talked about magnesium being biodegradable?
Yeah, that's a good thing, right?
It is, but the way it breaks down can be a problem.
How so?
If the corrosion is only happening in certain spots,
yeah,
it can weaken the implant.
Oh,
and that could lead to it failing too soon.
That's not good.
Not good at all.
But you said this could also be an opportunity.
Yeah.
I'm curious about that.
So imagine if we could control where the corrosion happens.
So instead of trying to stop it, you're trying to, like, direct it.
Exactly.
Shaping it to your advantage.
Exactly.
So how does that work?
Well, the MgO layer plays a big role.
That layer again?
Yeah, it's a key player.
So tell me, how does the MgO layer affect things?
Okay, so when the composite is in the body, it starts to react with the fluids.
Okay.
And a protective layer forms.
What's it made of?
Mostly magnesium hydroxide. But the MgO layer itself, it's not that resistant to corrosion.
Wait, so the layer that's supposed to be holding things together?
Yeah.
It can actually make the corrosion worse.
It can, in some areas.
That doesn't seem very helpful.
Well, it's complicated.
How so?
The MgO layer, it can act as a barrier.
Okay.
And slow down the corrosion. But it can also create little pathways.
Pathways?
Yeah, for corrosive agents to get in.
Oh, so it's like a double agent.
Kind of, yeah.
Working for both sides?
That's a good way to put it.
So how do they figure out which side is going to win?
That's what they're trying to figure out.
Okay.
They're using all sorts of techniques.
Like what?
Well, one is called electrochemical impedance spectroscopy.
Wow, that's a mouthful.
It is.
What does it do?
It basically measures how the material responds to electricity. And that tells them how the MgO layer is affecting the corrosion.
So they're looking at it like at the atomic level.
Exactly.
Wow.
And what they're finding is really helping them understand how to design better composites.
Composites that won't corrode as easily.
Right.
Okay, so we've talked about the microstructure, the strength, how it breaks down, and this whole localized corrosion thing. Is there anything else we need to know about this MGDBM composite?
Actually, there is one more thing.
Okay, what is it?
Remember how we were talking about the two different types of DBM?
Yeah, the one with the carbon coating and the one without.
Right, so the one without the coating.
Yeah.
It led to another interesting discovery.
Oh.
They found a new phase forming.
A new phase?
Yeah, an intermetallic compound.
Okay.
Called Mg2Ca.
MCOT?
Mg2Ca.
What is that?
It's an alloy of magnesium and calcium.
Oh, okay.
And they didn't see it in the composite with the carbon coating.
So it only formed in the one without the coating.
Right.
Interesting. But why does it matter?
Well, we're not entirely sure yet, but it could affect the properties of the composite.
Like how it breaks down.
Exactly.
So it's like a mystery ingredient.
You could say that.
This just keeps getting more and more interesting.
I know, right?
It's amazing how a small change, like that carbon coating, can make such a big difference.
It really can.
I'm really curious to hear about the applications of this MGDBM composite.
Yeah, that's the exciting.
It seems like it could be used for so many things.
It could.
We should talk about that more.
We should.
But I think we'll need more time.
Definitely.
We've covered a lot of ground.
We have.
But there's still so much to explore.
There is.
I guess we'll have to continue this deep dive another time.
Sounds good to me.
Wow, we've really been digging deep into this MGDBM composite.
We have.
It's amazing how much is going on down there.
At that microscopic level, yeah.
Like tiny pores, MgO layers, even that Mg2Ca phase.
It's pretty incredible how it all comes together.
It is.
And it's opening up some exciting possibilities for bone repair.
Okay, let's talk about those possibilities.
Okay.
Some of our listeners might be just tuning in.
Right.
So can you explain why this research is such a big deal?
Well, imagine this.
Yeah.
You break a bone.
Ouch.
And instead of getting those metal plates and screws, which can cause problems later on, you get this implant.
Okay.
It's biocompatible. Helps your bone heal.
Yep.
And then it just disappears.
Like magic.
Pretty much.
No more metal, just healthy bone.
Exactly.
That sounds amazing.
It is. It is.
No second surgery, no stress shielding.
All thanks to this MGDBM composite.
It's like they've engineered a perfect healing solution.
Whoa, we're getting closer.
It's like giving your body the tools it needs to heal itself.
Exactly.
And because it uses DBM, it's already designed for bone growth.
It's osteoconductive.
Meaning.
It guides new bone growth.
So it's not just sitting there.
No.
It's actively helping the bone heal.
Exactly.
But there must be some challenges.
There are.
What are the researchers still working on?
One of the big ones is controlling the degradation rate.
Oh, right. We talked about that.
We need it to break down.
Yeah.
At the same pace as the bone is healing.
So it's not too fast or too slow.
Right. If it's too fast, the bone won't have enough support.
And if it's too slow,
it could get in the way of the bone remodeling.
So it's like a delicate balance.
It is.
Like finding the right tempo.
Yeah, perfect rhythm.
And that's where controlling the corrosion comes in.
Exactly.
Making sure it happens at the right time and in the right places, like sculpting the degradation process.
That's a good way to put it.
So it's not just about the materials themselves, but how you engineer them.
And how they interact with the body.
Right. And speaking of interacting with the body.
Yeah.
What about those byproducts?
The ones from the magnesium breaking down.
Yeah, are those safe?
That's another thing they're looking into.
Making sure they don't cause any problems.
Exactly. They have to be biocompatible.
It's like making sure body is happy with the new tenant.
Like a good host.
So this research started with bone repair.
Mm-hmm.
But it seems like it could go way beyond that.
Oh, absolutely.
Like, what other medical applications are there?
Well, think about reconstructive surgery.
Okay.
You need materials that can integrate with tissues.
Right.
Or biodegradable stents.
For heart problems. They could just dissolve after they've done their job.
It's pretty amazing.
The possibilities are endless.
They really are.
It's like we're moving away from those permanent implants towards something more natural.
Something that works with the body.
And because it uses DBM,
yeah,
you could customize it.
You could.
Different shapes, sizes, even different degradation rates.
Tailor to each patient.
Personalized medicine.
Exactly.
That's incredible.
It is, but we have to remember this is still early research.
Right.
It's a lot more to learn.
Before we start seeing this in hospitals.
But the potential is definitely there.
It's really exciting stuff.
It is.
We've gone from tiny microstructures to this whole new way of thinking about healing.
It's been quite a journey.
It has, and it's all thanks to researchers like Dr. Escalera.
We're pushing the boundaries of what's possible.
So as we wrap up, let's leave our listeners with something to think about.
Okay.
We've seen how versatile this MGDBM composite is. Strong, biocompatible, biodegradable. What else could we use it for?
That's a great question.
Could it help regenerate tissues? Could we create biodegradable sensors?
To monitor healing.
Exactly.
The future is full of possibilities.
It really is.
It'll be interesting to see where this research goes.
And to our listeners, keep exploring, keep asking questions.
And keep diving deep into the world around us.
Until next time.